welcome. The topic we'll be discussing in this session is Amdahl's law and multi-threading models. So basically we are discussing about threads. So last class we have discussed the introduction of threads and what are the benefits of thread and what's the difference between concurrency and parallelism and what is data parallelism and what is task parallelism. So in this session we'll be discussing about Amdahl's law and what are the different types of multi-threading models available. Okay. So basically Amdahl's law is used to measure the performance gain by adding more cores to the system. Okay. So when additional cores are added uh, to a computer, then how much performance gain is achieved? So that is given by a formula, and this formula is called as Amdahl's law. Okay, and this is the formula. So speed up. So the speed up in the sense, the speed up of the processor will be less than or equal to 1 by s plus 1 minus s by n. Okay. So the speed up that is improved by adding more cores will be equal to this. So here there are some variables s and n. So what is s and what is n? So s represents the fraction of or the percentage of serial operation. So in a system, when a process is running, it may have two types of tasks. The set of tasks that can be done parallelly and the set of tasks that should be done serially. So serial portion in the sense, these tasks should be executed serially. Even though you have multi-processor system, you may have 4 processor or 5 processor or 4 cores or 5 cores. But these instructions cannot be executed in parallel. So how many such instructions are there? So that is represented as yes. So yes represents the serial portion of the instruction, the percentage of serial portion of the instruction. Okay. And what is n? N represents the number of processing cores. N represents the number of processing cores. So if your system has 2 cores, then n is 2. If the system has 5 cores, then n is 5. If the system has 100 cores, then n is 100. Okay. So let us consider a typical example. Let us assume that the 25 percentage of instructions are has to be executed serially in our system. Okay, let us assume that 25 percentage of instructions should be executed serially for a given process, and remaining 75 percentage of instructions can be executed parallelly. 75 percentage of instruction can be executed parallelly, 25 percentage should be executed serially, and let us assume we are moving from 1 cores to 2 cores, that is n is equal to 2. Current value of n is 2. Then how much will be the performance gain? So if you apply in this equation, what you will get in the sense, you will get a value of 1.6. It means that the performance will improve, the speed up will increase by 1.6 times. Okay. So this is the law using which you can calculate the performance gain by adding additional cores or additional processors. Right? So now we'll be discussing about multi-threading models. So basically we'll be discussing these multi-threading models uh, under 3 headings, or you can say there are 3 types of multi-threading models available. So what are the 3 types? So those 3 types will be, so these are the 3 types of multi-threading models available: many to one, one to many, and many to many. So what are those? Let us try to understand. So in a many to one model, many user process will be many user threads will be connected to one kernel thread. Many user threads will be connected to one kernel thread. So before that, what is a user thread and what is a kernel thread? User threads are the one that is created by the user process, and kernel threads are the one which is created by the operating system. And all user threads need to take the support of the kernel thread. A user thread cannot exist by itself. It should depend on some kernel thread. In a many to one threading model, many user threads will be mapped to one kernel thread. Okay, so this particular model has its advantage and also it has its own disadvantage. The advantage of this model is that you can create any number of user threads. That is not an issue because all the user threads are controlled by only one kernel thread. So I can create 100 user threads also, because basically I'm not requesting more resources from the operating system, because there is only one kernel thread which is going to control all these things. So that is the advantage of this particular system. But the disadvantage is one thread can block all other threads also. Say for example, this is thread T1. Let us assume currently this thread T1 uh, is is using the kernel thread. That is, it is performing the task through the kernel thread. Now say that this T1 got blocked. Now because blocked in the sense it may be waiting for an IO operation or something. So who is waiting? Along with T1, this kernel thread is also waiting. So it means that this kernel thread is not available during that blocked time. During the blocker time, the kernel thread is not available. So the other threads also have to wait. They also cannot continue. Thread 2 and thread 3 and thread 4 also should wait, because there is only one kernel thread you have. So when this particular thread T1 is waiting for an IO operation, it means that the associated kernel thread is also waiting. Okay, so uh, this is one of the disadvantage of this particular model. So it also has another disadvantage. Assume that your system is a multi-core system or a multi-processor system in which you have more than one processor or one cores. Okay. So say let us assume the system has three cores. So it means that you can perform three operations parallelly. Three operation truly parallelly. So there are three cores available or three processors available, core 1, core 2 and core 3. Now three actions you can perform parallelly, but this model restricts that you can use only one kernel thread. So multiple user threads will be mapped to only one kernel thread. So you cannot take advantage of the multi-core that is available in your system, because finally this kernel thread will be using only one core. Okay, so you cannot take advantage of the multi-core architecture or the multi-processor architecture that your hardware supports. That is the second disadvantage. There is no parallelism. It cannot support parallelism in a multi-core system, right? So this is how a many to one threading model works. The second threading model what we'll be discussing is one-to-one threading model. So in a one-to-one threading model, every user process will be connected with a separate kernel thread. Every user thread will be mapped to a separate kernel thread. That is, each and every user thread will be mapped to an individual or a separate kernel thread. So again, this model also has its own advantage and disadvantage. The advantage of this model is it can support parallelism. It truly supports parallelism. That is, if your system is having more than one processor or one core, then uh, then this particular model can take advantage of this, and it can ensure that all the cores are getting effectively utilized. So for example, if your computer is having three cores, then currently these four threads are running, four user threads and four kernel threads, because for every user thread there will be a kernel thread. So maybe the operating system may connect this kernel thread with core C1 and this kernel thread with core C2 and this kernel thread with core C3. Okay, two threads should be connected to core C3. Okay, so they will be context switching. Like if C3, if this thread may execute for some time in C3 and then this thread will execute. Whereas these two are running fully parallelly. Okay. So this is the advantage of this particular system. the more parallelism. So it supports more parallelism than many to one model. But the disadvantage of this model is that normally you cannot have many threads, because for every user thread you should have a kernel thread, and creating a kernel thread is a costly operation. Creating a kernel thread is a costly operation, because for every, whenever you create a user thread, you need a kernel thread. So 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 you cannot create a kernel thread just like that, because operating system resources are limited. So accordingly only operating system can create a kernel thread. So most of these systems will provide a restrictions on the number of threads that can be executed at a given time. Okay, number of threads per process will be restricted due to the involvement of overhead involved in the creation of the kernel threads, right? So this is how the one-to-one model works. And the next is many-to-many model. In a many-to-many model, what happens in the sense, many user threads are connected to many kernel threads. Many user threads are connected to many kernel threads. That is actually what it happens in the sense, more than one user threads or mapped with more than one user threads or mapped with either equal number of or less number of kernel threads. Okay, say you have 5 user threads. So these 5 user threads will be mapped with either 5 kernel threads or less than 5 kernel threads. Okay, so the number of kernel threads will be always less than or equal to the number of user threads. It will not be more than the user thread. So this is how the mapping does. Okay, that is, the number of user threads will be less than or equal to the number of kernel threads. Okay, fine. So what is the advantage of this model? So this model takes the advantage of uh, many to one model and one to one model. So in many to one model, the advantage is that you can create any number of user threads, because everything is controlled by only one kernel thread. But the disadvantage is it does not support parallelism. Okay. Whereas the advantage of one to one model is it supports parallelism, but it places a restriction on the number of threads that can be created by a particular process. Okay, so those are two extremes. So this many to many model, it takes the advantage from many to one model and from one to one model. Okay, so here number of kernel threads that you create is also under the control, under your control. Okay, because you can also connect more than one user threads to a single kernel thread depending on the resource availability, and also you can create any number of user threads. Okay, so basically it takes the advantages of the other two models. It allows the operating system to create a sufficient number of kernel threads, and basically it takes the advantages of the other two models. Okay, so this is how many to many model works. The and this two level model is one variation of many to many model. It is one variation of many to many model. So it is basically same as many to many model. Other than that, it adds one additional feature that a particular user thread can be bounded to a particular kernel thread. Okay, a particular user thread can be bounded to a particular kernel thread. What does it mean? It means that user threads want to be binded with only one kernel, one particular kernel thread throughout its lifetime, that feature is available. Okay, but that may not be available in a normal many to many model. For example, in the normal many to many model, this thread, let us assume this is connected with thread, this particular kernel thread, time being. This is thread 4. Thread 4, user thread 4 is connected with this kernel thread 1. But after some times, this thread 4 may be mapped with kernel thread 3. That might have happened. Okay, but uh, but two level model, what it ensures in the sense, it also provides a feature that a thread can be bounded to a user thread can be bounded to one particular kernel. So, so these are the different thread models that are available. So what we have discussed, in the sense, we have discussed the Anthol's law and the various thread models, many to one, one to one, and many to many thread model, right? Yes, thank you.